Okay, units of electricity. Well, we've talked a lot about this, but let's put some notes to paper here. So let's talk about current. Current. Current, the symbol is what? I. Symbol is I. It stands for intensity. If you must know why it's an I. I stands for intensity. It is measured in amps. Amps. Named after Andre Marie Ampere. So it's Ampere. A-M-P. No, I don't do stuff like that. That's not. All right. And we can define it as the flow of electrons through a conductor. So we want to remember that it's flow, like water. Well, this said, like water moving across a water wheel. I don't know. Yeah, it's the picture with the guy going through the pipe. So, all right. 1 amp here. So the full word is ampere, but I'm always going to say amp, is the rate of flow, of 1 coulomb, C-O-L-C-O-U-L-O-M-B, coulomb per second. And of course a coulomb, 1 coulomb, 1 coulomb is equal to 6.28. What does 6.28 sound like to you guys? What is 6.28? Come on, nobody recognizes that number? About pi times 2. Yeah, pi is 3.14. So I remember it this way. 6.28 times 10 to the 18th. Yeah, I got it right. Times 10 to the 18th power. That's how many. So what that is apparently somebody stood right there with a stopwatch and they counted all of the electrons that went through 1 ampere at 1 coulomb per second. So that's 6.28 times 10 to the 18th. So that's a lot of zeros. Am I going to ask you to remember that coulomb is 6 times 2, 8 times 10 to the 18th? No, I am not. Because I'm just not that mean. All right. But I would say current. What is its symbol? I would ask you, and you'd say it's I. And I would say, what's it measured in? You would say amps. And I would say, right. And we'd describe it. And you'd say flow of electrons through a conductor. And say, oh, you're doing good. All right. So B is voltage. Voltage, the symbol. Oops. Let's try spelling symbol correctly. S-Y-M-B-O-L. The symbol is E. And you're going to ask me why. And I'm going to write it right here. Its symbol is E because it is often called, or it used to be called electromotive force. Electromotive force, which is also EMF, abbreviated EMF. And we could do this. We could say think, E-L-E-C-T, electron moving force, which is not correct, but you could think that if you want. Electron, all right. It is measured in this is your cue to say something. Volts. Named after Alessandro Volta. Yeah. I don't make jokes. It is electrical pressure. Or as I say over and over, difference of potential. And that brings me to the resistance. There's some really good memes out there I should collect. One is like, join the resistance. symbol of a resistor. Yeah, there's one with the guy that's going, ohm. All right, resistance.
That's great.
The symbol is resistance. Symbol.
R.
R. For resistance.
Or the omega.
All right, measured in what? Ohms. O-H. Ohms. The Lululemon sign. Named after George Simon Ohm. That's for real. It restricts. Is it going to restrict the current or restrict the voltage?
Current.
Restricts current. But there'll be a voltage drop. Restricts the flow of current. Restricts. Well, I'm going to write that. The flow. The flow of current. And causes a drop in voltage, which is pressure. It can also be thought of as electrical friction. I'm moving on. Here we go. Nobody's freaking out. Okay, good. Oh, somebody freaked. Bad.
How exactly?
Don't worry. There it is. Right, it's back. There it is.
Sorry. How exactly does it resist the flow, or is that beyond the scope of this class?
Nobody really knows.
Okay.
When I say nobody, I mean everybody knows. It runs through a component that, well, I'm just using the words to define the words. I hate it. But like your resistors, they're made of carbon film.
Okay.
And so it doesn't allow electricity to flow quite as well.
Okay.
And they can make it different ways. Carbon is one of the things that you use often. Like you can even make a variable resistor. And so do like a variable resistor is carbon stacks. And so put these carbon stacks in something and you push it together really hard and there's really good connection. And then you have little resistance. And then they'll kind of relax the pressure, and then they get space between them, and they're not pressed together, and so then there's less resistance. More resistance. Yeah.
So with the current voltage and resistance, I don't know if I'm getting ahead of myself, but if it's measured by decimals,
In decimals, yes.
you know what you're looking for? Or
Do I know what I'm looking for?
Yeah, as far as the,
Oh, I'm looking for.
as far as
Good
the
time.
project.
Right.
I'm just looking for
Okay. Probably the most difficult question I get asked is that one because I don't have a really good answer. And this question is basically, how many decimal places should we go to? Okay, so if I said 2 decimal places, then you would say, fine, it's 0.001 amps. And you go, well, I just did it 3 decimal places. Okay, but the next guy is going to go, well, wait a minute, I'm going to go 1.326 milliamps. And, you know, it's hard because where do I say it? If you're doing it amps is one thing, it's milliamps is another. So I don't have a standard answer for. Try and be as accurate as you can, but don't be ridiculous. I don't write down more than 3 decimals. Maybe that answers your question. Maybe I should just say that. Okay, so, almost read this. So most important, simple circuit. So that's really all we had to know. We had to know resistance, volts, amps. What about watts? I'm getting to that. Apparently. I was wondering when I'm going to say it. I don't know why there. I don't know. I don't know why I put it later, but I'm doing it over here. So a simple circuit. Maybe because I want you to walk a little bit before you run. Simple circuit. All right. Must contain, let's say 4 things. Must contain 4 items. All right. Simple circuit. Who can tell me what 4 items I must have in a simple circuit? Give me one.
Battery.
A power supply.
Resistance.
A power supply. All right, so I got a power supply. That is my source of electrons. Source of electrons. What are some sources of power supply?
Battery.
Battery.
Wall outlet.
A wall outlet.
Car battery.
Somebody said battery.
Lightning.
Okay, car battery. Don't say D cell battery. A cell battery. Okay, no. Okay, so batteries. Well, the sun then has to go through volts to the panels and stuff. Okay, so generators, alternators. Where does it come from the wall?
A big power.
From a big power source, which is spinning magnets across wire. Oh.
I think we went to get Bill. Big ass battery. Oh,
My
here's your
power
battery.
source.
Yeah. Oh.
Oh.
It is nothing more than a couple of magnets on the end of a Tinker toy with wire wrapped around the outside.
Should work.
Battery?
You see light bulb light up?
Oh, yeah.
Hit the light.
Hit the light.
I got it.
You should take that to
Just battery, it's just magnets running across wire. That's all electricity is. So flick them back on.
That's cool.
So something that simple. So power supply, source of electrons. All right, what else do I need? Here we go. Here's my power supply. That is a battery. That's a multi-cell battery. I told you that's the positive, that's the negative. All right, what else do I need? Not a ground. Conductors. Okay, we'll go with that. Conductor. Conductor. All right, so here's a conductor. Got a conductor, got a power supply. What else? Okay, resistor or a load. Now I'm going to, not just me, we often draw resistors, just we put it, but it's a load. I can say, well, that's, it could be anything. It's my load. All right, all right, I got power supply, conductor, resistor, load. What's my last item?
Need a closed circuit.
Path. Very good. Path or closed circuit, because this is not going to have any flow. That is a switch, which I don't need. Do I have a complete circuit?
No.
Nope. Now I do. So if I remove the power supply, that becomes rather obvious why it doesn't work, because I don't have a source of electricity. If I remove a conductor, you can see that that's very obvious. I do not have a path, and so if you don't have a path for electrons to flow, they don't flow. Why do I need a load? Wouldn't it be a simple circuit without it?
What would it be powered?
Well, is this not a simple circuit?
That's a short circuit.
That's yep. Well, in a minute, it's going to start smoking and turning red and getting melty, and then it's going to open. So, and then it's not going to be. So maybe it would be a circuit for very few seconds, but that's it. So that's why we need all of those items. There we go. Yes.
Do you need a resistor or a load even if the power supply that you're using has very low, like, watts of voltage?
Nope.
It always.
It may not melt, but it's like if you have an almost dead battery, probably won't damage the wire, but if there's enough, it'll make the wire very hot.
Then the wire becomes a resistor.
Yes.
Yeah. So what's the resistor on your power supply?
What is the resistor on what?
On
The Tinker-
On your
That's a power
Oh.
supply, not a circuit.
The wire, the windings of the wire. That was a good question. Where was my resistor? There's just enough wire on there, resistance wire. Good.
So if it had less wire on it, would it be easier to
Okay, hey, I will tell you that if I hooked up like a drill to this and really started going, this wire would get really hot. It really would.
So it's like
Let's try it out.
half of the circuit should be full circuit.
It's there's just not enough resistance in there to run it for very long.
Don't bulbs count as load?
Yes, bulbs do count as the load,
So,
but it would still get warm. But in mine, thank you. I don't know why I didn't just tell them that. So this is what mine looks like. There's my load.
Light bulb.
Light bulb. Light bulb.
You got an idea.
All right. If I don't choke and die. All right.
Wow.
Okay, that brings me to
So
Ohm's Law. Why did I just do that? I don't know. Ohm's Law. Named after the famous Dr. Albert Law. That was a bad joke, sorry. Ohm's Law, named after Albert Law. All right, never mind. Named after Ohm.
It was funny.
All right, thank you. Okay. Thank you. That's all I needed to hear. That was good. There's your Ohm's Law formula wheel. All right. All you have to do is memorize all of this.
nice.
I stands for what? Current. R stands for? E stands for? P stands for? Watts or power. Okay. This is what I'm going to teach you. And I'll help you memorize everything you need to know. Can you remember that? There, you're done. Almost done.
Awesome.
You only have to remember one other thing. Who likes pie? If you like pie, if you can remember E, I, and R, comes a nice little triangle like that, and you can remember that at least I like pie, you're done.
Hell yeah.
Okay? And here's why. Because all you have to do is cover up what you're trying to figure out, and the answer becomes obvious. So I'm going to go here to my laser. So if I want to know E, E is what? Voltage. I'm going to cover up E, and what's left? I times R. If I want to know E, it is I times R. If I want to know I, it is E divided by R. I want to know I, it's E divided by R. If I want to know R, it is E divided by I. R, E divided by I. That will get you everything you'll ever need to know. And what I do, even to this day, if I'm going to start working some sort of problem, or I'm trying to figure out a circuit, I write EIR. I don't put the little triangle, but I just take my pen, I go EIR. I write it right on my paper. I'm not afraid to do it, so you don't be afraid to do it either. Sometimes I can look for your paper. They write it down for me. Because it's just easy. It's a visual representation of what I'm looking for. All right, and then I want to know power, so I cover up the P, and I got I times E. That's all you got. I can't think of a single situation in at least my entire class or my career working in aviation where I had to worry about the square root of P divided by R, or E squared divided by P, or P. You see, there's a lot of this other stuff, but this right here, it gets you through everything.
So, if you were to do E squared divided by R, and then also do I times E, would that you still get the same answer?
Yes. Reasonably close. There'll be some rounding issues probably sometimes,
Yeah, okay.
but for the most part, yeah, absolutely.
What book is this in? Or probably what? I guess this figure. What book is it in?
Figure 10-43, Ohm's Law. I don't know. I think it's probably your general, but it's going to be the wrong page because this is the previous general.
Okay.
Because it just switched like last year. So
Okay.
I still work out of the pre-A model.
It's chapter 12, right?
Yeah, and they just change chapters all over the place.
Okay.
Yeah, and the one in the tool room, which is the older one, it's in chapter 10.
That's right, 10-43.
The new one is 12.
All right, but it's EIR, PIE, done. Just done. All right, so Ohm's Law. Ohm's Law. What am I going to say about Ohm's Law? All right. Well, that's just being redundant here. Although I did put Ohm's Law, then I have units of electricity, and I just got redundant. I said volts is E, amps is I, resistance is R. We wrote that volts. Review. Volts E, amps is what? Thank you. I. Very good. You guys are just a little bit behind me. Resistance. R. What's a pirate's favorite letter? That joke. Nah, it'd be the C. Sorry, I just Thank you. I'll be here all night. And watts,
That's a good one.
named after James Watt, which is E times I equals the watt. We're going to talk a lot about watts. We're going to use them all kind in engines. We're going to use watts quite a bit. And Ohm's law states. Put this here. That can be A. This can be B. B. Ohm's law. Ohm's law. What does Ohm's law actually say? It is the current in an electrical circuit is directly proportional to the EMF, which is voltage. I'll tell you that. And inversely proportional to the resistance period. So Ohm's law says the current in an electrical circuit is directly proportional to the EMF, and which is voltage, and inversely proportional to the resistance. Would you like me to translate?
Yes.
Yes.
please.
Okay. As the voltage goes up, all the other things being equal, the current goes up. So as voltage goes up, current goes up, assuming the resistance stayed the same. We see current is that's what proportional. So the more the voltage goes up, the more the amps are going to follow it. And then the next portion is and inversely proportional to the resistance. So as the resistance goes up, the current
Just down.
goes down.
I was worried you'd say up, and then I'd look really
I was going to say up, yeah. Up! And then you're like, what? No, there's everybody else. That's what that says. And Ohm, Mr. Ohm, also says 1 volt. You know what? I bet you any money it was really Mrs. Volt who came up with this. Causes 1 amp, so I'll make that a 1 volt, causes 1 amp to flow through 1 ohm.
1 volt causes 1 amp to flow through 1
1 ohm, yep. And if we think about it, 1, 1, 1. So cover this up, 1 times 1 is 1. 1 divided by 1 is 1. So it's just the way it is. And then we looked at these formulas already with the E, I, and R. So E, I, and R, which is to say that E equals I times R. I equals what?
E divided by R.
E divided by R. And R is,
E divided by R.
very good, E divided by I. And we'll just throw this one in. P is equal to I times E. I like pi.
Who's first on the scene with this? Was Ohm first? Was Volt first?
I don't know. Rich, were you there? I wasn't.
I was there.
He was old.
Yeah.
E squared divided by R would be usually the same.
All right. So, okay, I'm going to scroll down.
Yeah, that's what I was saying. E squared divided by R.
All right.
I times R.
So a little more about power. I like power. Power! Power. Who likes Grand Tour?
Yeah.
Okay, if you so much as mention it after you've seen it and I have not, we will have a problem.
Got it.
So it's the only real rule I have. Don't mention Grand Tour. I have to save it till my son gets home, and we watch it together. So sometimes I can't watch it for a long time until we get together.
That's too bad.
I know. Okay, power. Power is the watt, which is power. That is, well, I already told you, it's P equals, I'm going to say I times E because that looks like pi. It is, do I want to do this? Well, okay, sure, why not? It is 0.00134 of horsepower. You don't have to remember that. Why am I telling you this? You're crazy.
Should I look away?
And since, yeah, look away. And 1 horsepower. Everybody know what a horsepower is?
Yeah.
How much is a horsepower?
1 horse.
No.
746 watts. And it is the amount of energy, of E-N-E-R-G, energy required to raise 550 pounds, a distance of 1 foot in 1 second. Would you like to know how they came up with that?
Yes.
All right. And by the way, what kind of horse must it be?
Stallion.
It must be an English workhorse. Okay, this is actual truth, as best I know it. But it is true, it's an actual workhorse. So James Watt, he was the inventor of the steam engine. And so he wanted to sell the steam engine to the mining companies. And I hope I'm getting this mostly right. I know I'm getting it mostly right. So he wanted to sell the steam engine to these mining companies that replaced the workhorses that they had. But it was very difficult for him as a salesman to say, well, if you have my steam engine, you would need less horses. And then, of course, the people say, well, how many less horses? And so he had to come up with this formula. And so he actually figured out how much this English workhorse could do. And then he would translate that into what his steam engine could do and say steam engine was equivalent then to 1 horsepower, 746 watts. And then he sold the steam engine to the mining companies, and that's kind of how it all worked out. I have dangers of electricity, but I already told you about this. Yeah.
What is, it says amount of energy to raise
50 pounds, a distance of 1 foot in 1 second.
of 1 foot in 1
1
second.
foot. Sorry, I get to the end of my board, and it's kind of hard to. That's my story, and I'm sticking to it. All right, now we're going to get into some important laws. And once we do that, we're going to be able to put together some circuits. So, you see, that is redundant. Series circuits need 4 things. They are? Power source. Conductor, load, and a path. Okay. The current. Oh, this is going to be for series circuit. Series circuit. Well, maybe I should define a series circuit. What is a series circuit?
Circuit with only 1 path.
Only 1 path. And what is a parallel circuit? More than 1. All right. I'm going to talk about series circuits right now. This only applies to series circuits. So number 1, the current. Current. What about the current? It is the same in the entire circuit. Which is to say that I total, so that's I, and this is sub t, so that's total. I total is equal to I sub 1, which means the current through resistor 1, which is also equal to I sub 2, which is equal to I sub 3. And what I'm talking about, if I drew a little picture, it might help you just a little bit. I'm just going to go right there. If I draw a simple circuit that you can see, and this is a what? Battery. That's a battery. And this is a what? Resistor. I'm going to draw another one here. one more here. And up. When I have you draw your circuits, number one, it must look professional, not like that. And the reason why it's important for it to look professional is at some point you're going to realize that when you're doing work on aircraft, especially if you're doing major alterations and repairs or anything to an aircraft, you have to make a drawing of what it is you're going to do. That drawing becomes part of that permanent aircraft record in Oklahoma City. So in theory, if the aircraft is still flying 100 years from now, one of your relatives is going to pull up some documents and go, would you look at that? It's my great-great-grandma Steele. And she made a drawing. And isn't it pretty? And then they might look at somebody else's and say, oh, look at that one. No, never mind. Don't look at my grandpa's stuff. It's pretty nasty. So, but in this class, I want you to do E, I, R, and P a lot of times. This is the total. And I want it over here, here, or over here. This is probably better. E, I, R, P. I just didn't have enough room. Total. Total. And see, that's my total right there. And this is resistor 1. Resistor 1. And you have E, I, R, and P for 1. So that's sub 1. This over here is 2. So we have E, I, R, P, sub 2. And E, I, R, P of 3. So when I say that the current is the same in the entire circuit, so I total, the total current is the same as in 1, is in 2, is in 3, and I can say so on. And I can add 1,000 resistors, and that would be true. And then I would say that oops, I need to move this. I'm out of room. 3, 2, 1. All right, nobody panicked. All right, I'm good. All right. And then I would say the voltage. This is the voltage in a series circuit. Voltage is voltage total is equal to the voltage of 1 plus the voltage of 2 plus the voltage of 3, on and on and on. And the resistance. Resistance total is equal to the resistance of 1 plus the resistance of 2 plus the resistance of 3, on and on and on. So in the interest of time, which we have very little left.
I have one question. You said the current is the same in this entire circuit.
Mm-hmm.
So is the voltage, does the voltage change?
Yep. I'm going to show you that in just a minute.
Okay.
That's a good question. All right. That's all you need to know. So don't worry about that. It's on the test.
Okay.
I'll just draw a picture and say which one is. It's on the test. You will have to decode resistors for those of you who haven't gotten to electricity yet. However, I'm just going to leave that to you. This is all in your workbook. If you have trouble, figure it out. Who are my Android fans in here? Okay, I don't know about Apple, but there are 2 apps that I recommend you get. One is called Electro Droid.
Can we pull out our phones?
I love this. This is the best class I've ever had. And that's the only problem is it's on your phone, but you can pull out your phone right now. Is I use that app. You'll see me using it in class to check you because I just tap the color and it'll tell me. And it's got a lot of good information on it. And the other app is called a mag flashlight, which I love using, especially for NDT stuff because it's a high intensity magnifying glass on my phone that takes pictures and saves it. So use it.
First one?
Electro Droid.
And here for Apple, it's a resistor.
Resistor? Okay.
Yeah, for Apple, it's called resistor.
So if you're using a tablet or a pad, I will let you, to a certain extent, use that tool,
Yeah, got that sort of
except I won't on the test. So I would not even bother right now. I'd say, well, you got to learn this. Because on the test, there'll be something on the test to ask you to decode resistors on the test.
You're not going to give us the chart on the test.
Yes, of course I would. Oh, that's a good question. I don't mean to laugh at you for asking that question. That was a very fair and honest question. I would never expect somebody to try and memorize this. I won't memorize it. I'm not putting my time and effort into that, so I won't expect you to put your time and effort into it. So if I won't do it, you don't have to do it.
You graded mine. I could have sworn I was like, this guy memorized everything.
No, I have my.
No, but I didn't know that you were doing it off of that. I was just like, I thought, because I saw you with a pen.
Oh,
I thought
and
you were
some of
writing
them.
everything
Okay,
down. I was like,
some of
this
them I
guy-
do have memorized. It's just because you see the repetition so often. Brown, black is 110. And it's just, one. It's I see it so often. I know what I'm looking for. So, all right. So you're gonna have to do that. Let me think here. I have a few more minutes. All right. So where I want to go with this is where I wanted to go from the beginning. Is that we have to, you and me, what you have to do is you have to be able to compute and figure out circuits. And so what happens with this voltage drop? Now, if I make a very simple circuit, and I said that the voltage is 6 volts, and I said that the current, and the resistance is 5 ohms. I'm just making up something. It's 5 ohms. I'm going to say E, I, and R. I would have to figure out what the current is. If I just gave this to you, I said, there, 6 volts and 5 ohms. Figure everything out. Fill in everything there is in here. This is what you need to be able to do. But it's quite simple. It's just a simple little puzzle that you have to stop and look at. Sometimes there's multiple ways to solve the puzzle. Sometimes there's only one way to solve the puzzle, but it's a simple little puzzle. So you ask yourself, and I know I'm talking to me because I recognize my voice and I'm wearing my underwear, so it must be me. You always want to look for 2 out of 3. If you know 2 things, you can always find the third. If you know 2 things, you'll always find the third. What 2 things do I know? I know E and I know R. Total. Therefore, I must be what?
Genius.
Okay, I want to know I, so I go E divided by R. E, 6 divided by 5 equals 1.2 amps. Okay, what else do I know now? I know that the current in a circuit, series circuit, is the same through the whole circuit, right? Therefore, I know that this is 1.2 amps over here. But there's only one resistor. And I know the ohms of this resistor, the resistance, it's 5. And doing the math here, so what is E? Well, it is E equals I times R, and guess what that is? It's 6. Okay, so if you only have one component, the totals are also equal to that component. Because what this is saying is you have to have a full voltage drop of 6. So if I put the voltmeter right here, it's going to say 6. If I put the voltmeter here, it's going to say 6. If I put the voltmeter here, it's going to say 0. All right? If I break open the circuit right here and put in an ammeter, it's going to say 1.2 amps. If I put it over here, it's going to say 1.2 amps. If I put it here, the amp meter is going to say 1.2 amps. Crickets. Hear crickets? All right. But sometimes it makes a little more sense if you're looking at multiple components. So if I have multiple components, so I have E, I, and R. E, I, R, and E, I, and R. And I said, well, this one's going to be, I'll say this is 3 ohms, and this one can be 6 ohms. I'm just making stuff up here. And this can be 12 volts. All right. So I'm going to ask you to solve something. This is very simple. Ask you to solve something like this. We just look at the puzzle. And the rule, if you know 2 things, the third is, you always find the third. Sometimes that's not the case. Like, I only know one thing here. I only know one thing here. I only know one thing here. Can I solve any of these? Nope. I can do nothing there. What can I do?
Total resistance.
Total resistance is exactly what I can find. So I told you that this has 6 ohms and this has 3 ohms, and you know that R total equals R1 plus R2 plus R3, on, but I only have 1 and 2. So what is my total resistance? Okay, 9 ohms. Now I've got two things, and I can find the third. So how much current do I have? I want to know I, so it's E I R. So I want to know I, it's E divided by R. E divided by R. What do I get, Christian?
1.3.
1.3 what?
Amps.
Okay, I just want to make sure. Okay, okay, now what can I fill in? What else do I know about this? The current in a series circuit, I total is equal to I1, which is equal to I2. So that means the current here is what? 1.3 amps. What's the current here? 1.3 amps. If I know two things, I can find the third. What is the voltage here? You guys got this is interactive.
3.9.
I hear two people. Have you guys checked out on me?
It's 3.9 volts.
1.3
Oh shit.
times
3. Yeah.
3 equals 3.9 volts. 6 times 1.3, 7.8. Have you guys already checked out on me? Well, they're not paying attention, so go ahead. You gotta have some interaction. All right, I want to show you this. I also told you that E total is equal to E of 1 plus E of 2 plus E of 3, on and on. Notice that 3.9 and 7.8 equal what? Siri, what does 3.9 plus 7? You guys got his phone out over there? What does that equal? 11.7, which is almost the same as 12 if we didn't have rounding errors. Okay, so that is to say that the voltage drop across these two must equal the total voltage. So what's happening here is if I put a voltmeter right here, how much is it going to read? 12. If I put a voltmeter right here, how much is it going to read? 3.9. I just told you that. Okay, so what's happening is we are losing voltage across here. It's dropping. The voltage drops. So I'd say the voltage drop. What is the voltage drop across 1? You'd say, oh, it's 3.9. The voltage drop is what it measures across that. So we have a difference of potential between this point and this point because of this resistor down here. All right? So if I put a voltmeter across here, it's going to say 7.8. If I put one from here to here, what's it going to say? 12, because it's the same wire as right here. Just because I moved it down a little bit didn't change much of anything. All right. Yeah, I don't want to get too hard on you. Okay, so this is something.
What would be the other side?
I know. I was just saying, should I do the other side? What would the other side be? What would the other side be?
3.9.
Is that a voltmeter?
Voltmeter. What would this voltmeter say?
0.
Why would it say 0?
There's no difference.
Because this wire is the same wire, and it's the same as going right here.
Oh, okay.
So there's no difference in potential, so it's going to say 0. All right, looks like you guys are done.